Okay, chapter 16 in your textbook is talking about acids and bases. Now, the idea is acids and bases were already introduced in Chem 1411. But I'm going to go ahead and we'll go quote unquote back in time and reintroduce acids, right? So in 1411, you should have learned about two major types of acids. When we're looking at acids, right, the way we're able to recognize an acid is usually the format of the formula is you have a hydrogen and some kind of nonmetal. When you have a hydrogen combined with a nonmetal, for example, I'm going to give you guys a short example here, HCl, the common acid that we currently have in our stomach that's digesting our food, hydrochloric acid. This tends to be called a binary acid. And it's called a binary acid because most of the binary acids are made up of two components, right? Two elements. You have the hydrogen and then you have a nonmetal. Okay, now, even though this is classified as binary acid, there is an acid, which is example here is HCN, amongst many, that is classified under binary, but it is made up of three elements. At this point, I just feel like the day that these scientists were coming up with these classifications and the names, it was Friday. So everybody was tired and like, we don't want to come up with a whole new group. So we'll just call this binary. And then if you think about it, when this breaks apart, it does break apart into two ions, right? You have H plus and then Cn minus. So maybe that was the reason why, right? It's made up of a combination of two ions, but yeah. So we have a binary acid, this is one type of acid, and then the other one is called oxyacid. So how do we identify oxyacids? You recognize, you ask a hydrogen, a non-metal, and an oxygen. Not necessarily in that order, but those are the components in the oxyacid. Okay, so we covered that in Chem 1411, General Chemistry 1, binary and oxyacid, like I mentioned right here. Binary, you tend to have mostly two elements, hydrogen and a nonmetal. Oxyacid, it has to have oxygen for it to be classified as oxyacid, and so we have that. Okay, so what we're doing here is defining acids, right? And I classify these based on when we're going to be covering this a lot. So let me go ahead and cover this part real quick so I can go ahead and erase it. So in 1411, the definition we had of an acid was, and the base, was consistent with the scientist Arrhenius definition. Okay, so we'll go over it again as though we never covered it. In 1412, most of the work we do here focuses on Bronsted-Lowry definition. We'll go over that definition too. Plus, we are introducing this in 1412. Then in organic chemistry 1, you will look at Bronsted-Lowry again, but then you spend most of your time on Lewis acid and base definition. Does that make sense? So this is just telling you that 1411, our focus was on Arrhenius definition of the acid and base. 1412, this is the class we're in right now, Gen Chem 2. Bronsted-Lowry will be our main focus because that has to do with equilibrium. We will get to it later on. And then, of course, we have Lewis acid definition. The main time, well, I guess most of the time in organic chemistry, at least one, if I remember correctly, is spent talking about Lewis acid and base definition. Okay, let me go ahead and erase all these marks here so I can go ahead and reintroduce this. Okay. In 1411, when I was talking about the atom and the different atomic models, I was telling you that essentially when you have different ways of accomplishing one task or different scientists defining the same thing, it's almost like speaking to different witnesses of an event. And each witness is telling you their account of what took place, right? Based on their experiences, their level of knowledge, their level of detail, their personality plays through. So all of that comes in, right? Now, in this case here, we're not seeing the personality of the author, but we're seeing, oh my God, I'm trying to erase this while I'm talking. It's not working. Okay, I guess it's better. Sorry, trying to multitask is not working. Okay, so over here, we're looking at three groups of scientists defining what an acid and a base is, right? And so we go from the more restrictive definition, which is Arrhenius definition of acid and bases, and it's more restrictive because of what it's focusing on. So let's start with that. Okay, Arrhenius definition. This tends to be the simplest definition. It's easier to tell an acid is an acid according to Arrhenius, right? Because all we have to do is observe the formula and we're looking for certain elements presence or ions presence. And based on that definition, we can then make a judgment that, hey, this formula here is an acid because it has the following ion, right? But it also tends to be the most restrictive because any formula that doesn't have the ion cannot be classified as an acid. Okay, so we're told here acids are substances that when dissolved in water, so apparently we can't tell an acid is an acid outside of water, though we can kind of speculate, we can hypothesize in the formula. But when acids dissolve in water, they produce a hydronium ion or a hydrogen ion, right? The old school definition was a hydrogen ion. So what Arrhenius is saying here is for a chemical to be classified as an acid, first of all, it has to have an H in the formula, right? So it has to have a visible hydrogen ion. For example, HCl. Again, that's going to be my go-to. And when that HCl is placed in water, right? So you place this in water, or just sometimes it's written as AQ. Let me go the old school way, AQ, as in it's already in water. The water causes the hydrogen ion to separate from the chloride ion. Since the hydrogen ion was made in water, that qualifies this to be an acid, right? So whatever we judge to be an acid has to visibly have a hydrogen ion present in the formula, even though the ion, the positive part may not show in the original formula, but it's understood that whenever the acid goes in water, the hydrogen ion is released, okay? So what we're looking for here is a visible H in formula. They didn't really say that, but it's kind of implied, okay? And this will classify the formula as an acid. But once again, it's important to remember, just because a chemical has an H doesn't make it an acid. The chemical has to be able to release that hydrogen ion in the format of hydrogen positive, right? Or if you're writing this the new way, which is adding it to water, it has to release the hydronium ion in this form. So the hydrogen ion gets released by itself, or it gets incorporated with water this way. So let me try to explain that part here. This is the example or illustration of Arrhenius equation. This is the example right here. There are two ways to write this. The old school way, depending on the author you're reading, either way is fine. The author may just put the AQ here. If the AQ is put here, it's implied that HCl is in water. And you can see how the H plus gets released as an ion right here, and then the Cl gets released. So the ion that is responsible for acid behavior is this right here. So say this, this right here will be the acid ion, okay? So just because the formula has a hydrogen does not make it an acid. For example, okay? So this is then an acid. So while I'm here, just in case you're wondering, let me give you an example of a formula, sodium hydride, right? This obviously has a hydrogen in it, right? It's easy for us to speculate and say, hey, this is an acid. Well, if you somehow ionize this, you get sodium positive and then hydride negative. So this one right here is not a proton, okay, which is what H plus is also called, or H plus, therefore not acid. So going back here, we can see this is not an acid. Even though, yes, you can see that it has an H here, you can presume that the H will form an H plus, but when you actually ionize this, it doesn't form an H plus, it doesn't form a hydrogen ion or a proton. That's what this is called. It forms a hydride, right? Negative ion of hydrogen. And in that case, this is not a proton, therefore this is not an acid, okay? Acid has to be able to release hydrogen ion in water. Since the requirement is met, this can be classified as an acid. This looked like it could be an acid, but it's not because it didn't release a hydrogen ion. Does that make sense? It has to be a positive ion. Okay, let me go back to here. The other way of writing the equation that shows the ion that's produced is right here, a big or. The more new school way is saying the hydrogen is added to water, and then you have your one-way equation, one-way arrow, and then this forms H3O plus. What you're seeing here is the hydrogen ion is released, but it combines with water, right, to form H3O plus and then plus Cl minus. So this is called hydronium, okay? For the sake of this chapter and all other chapters, the hydrogen ion, which is called the proton, is equal to hydronium ion. Okay? It's just specificity. Like one author is trying to communicate that the water is implied. It is present, but they didn't feel like showing it. And then another author is more precise, and this person wants to show everything that's present, the actual species, right? So here I want to say the water is implied, that is present. With this one here, the water is shown. But they're technically the same thing. Does that make sense? Because as a student, that was confusing to me because I didn't realize that it can be written more than one different way. So then I thought, I don't know. I figured it out eventually. It was just one of those things where there was figuring out to figure, right? Chemistry, a lot on the mystery part. Okay. So once again, these ions are the ions that represent all things acids. So acids will be defined by the presence of either of these ions. Does that make sense? Can we move on now? Okay, let me go ahead and talk about, did I define that here or is this something else? Let's talk about base. Now with the base, right? Oops, no, let me continue with this one here. With the base, Arrhenius says that the base is a chemical. It has to contain an OH ion, but that's not the only requirement. A base must contain the OH ion in the formula. So you have to see the OH. It has to somewhere be, OH must be visible. Okay. Number 2, in water, comma, base must release OH ions. So usually with the Arrhenius base, once again, so must contain an OH. It's going to be visible. It won't be implied. It will be seen. And then in water, the base must release the OH ions. So the example I'm giving you here, now I can safely say sodium hydroxide. This is a base. Now, when it comes to base, I don't really know why. I just know that we never did add the base to water. It's always just a one reaction like that. You ionize this and you get sodium ion and then hydroxide ion, and that is the end. I'm thinking because in the experiments, they only see one type of ion representing base, right? So OH ion, this one here represents base. Well, remember I told you that both of these represent the acid, right? Okay, so you can see since this was produced, check, base, ion produced, therefore this is classified as base. And that's the end for the definition, okay? I'm trying to think about what else I can talk about here. Yeah, once again, the acid has a visible hydrogen, the base has a visible OH. Oh yeah, I was gonna tell you guys about a chemical that is not a base. An example of that will be sugar, right? Sugar is, I'm gonna go with glucose C6H12O6. Okay, so for the glucose formula, we have this right here. I'm trying to see, like that. I'm trying to draw this out like that. We have an OH here. We have a C, we have H. I think there's an OH here. This is going to be an H. You can see there's a bunch of OHs, right? So we got 1, 2, 3, 4, 5, 6. Oh my goodness, there's a lot of stuff here, right? So we got OH, we got OH, we got H. I don't necessarily have this formula memorized. I'm actually just, right. Okay. So you can see in the glucose formula, there's a bunch of OHs. Let me highlight all the 8 OHs we have present. This one here, this one here. Oops, not that one, not one. Go back, go back. This one here, we got this one here, we got this one here, and we got this one here. So when you have glucose solid and you place it in water, it becomes glucose aqueous. The OH doesn't necessarily separate, right? So these OHs remain intact. And because even though, so I'll say from this one here, making a judgment, right? Glucose has OH in its chemical formula. But does not release it in water. Therefore, it is not a base. Okay. Remember, the requirement is have it, check, present, right? But then also release it in water. So even though glucose has a bunch of OHs, it doesn't release it in water. Therefore, this is not base, right? Even if you write the formula out like this, it doesn't qualify as a base because the requirements were two: have it, release it in water. Having it alone is not enough to classify as an acid or base. Okay. Okay. As I mentioned to you guys before, I decided to leave some of my notes. So in Arrhenius definition, acid has an H plus in the formula, as I mentioned to you, is a visible H plus, right? And the acid can either be binary with mostly two elements, hydrogen and nonmetal, or oxyacid. I'm going to rewrite this differently because most of the acids, at least the inorganic acids are written like this, NMO, like that, like H2SO4 is hydrogen, the nonmetal, then the oxygen, in that order. So, but it doesn't matter. Either one was fine. But for the most part, back to Arrhenius definition, the hydrogen appears first. You can see right here in the binary and the oxy, right? So for most inorganic acids or acids that we cover in general chemistry, the hydrogen is written first. The nonmetal identity, as it says right here, the nonmetal could be any one of these. It could be sulfur, fluorine, chlorine, iodine, phosphorus, selenium, just a lot of different nonmetals, right? Our example we're seeing here is HCl, HF, H2S. These are all examples of binary acids. And then for the oxyacids you're seeing right here, HOCl, HCl, or HClO, it can be written either way. HBRO, H2SO4, right? And so this is showing you what's going on. Now over here, okay, I just noticed something I didn't think about before. So what we're having here, okay, I know I mentioned to you guys before was that with Arrhenius acid, it has a visible H, right? And the H gets released in water. So in many cases, by looking at the formula, like if I was learning this for the first time, I'll be like, wait, this formula here is an acid and a base. It's actually not. It's an acid. Well, how would I know that? When this is put in water, the bond breaks here, releasing the H plus. Now, if somehow the same chemical, when put in water, if that bond broke here, we have to follow the rules and classify it as a base. Does that make sense? But that's not what happens. And that's why lab is very important, because lab is the one that many times gives us more experience with the chemical for us to place the chemical in the right group. So what we notice is, even though this acid ends up having an OH here, when placed in water, when they test the solution when it's in water, what they get is the confirmation that an acid is present and not a base. I hope that makes sense, right? That means that H plus has been released and not OH. I never thought about that until I was actually reading something that was already drawn. Okay. Same thing with all the other ones, okay? Okay, so how will this be tested in lab? When you're working in the lab, acids that actually release H plus, tend to have a low pH. So you can use a pH paper or pH strip or a pH meter. The pH meter will tell you the exact pH with decimal places and stuff like 3.4 or whatever. The pH paper, since it's a strip and you're going to put it in a solution, it will change color. The best you can do is compare the color from the changes with a scale that's given to you, right? And then connect the color of the pH strip. Let me see if I can find this somewhere. I'm trying to be a little bit more tech savvy. Let's see. pH paper. Okay, so anyway, this is what I found for right now. So you have the pH strip, right? And then once you place the strip into the water, it then, sorry, then it changes color, right? And you want to compare it with the scale, and the scale will tell you approximately what the pH is, right? This is all I could find, y'all. It's been a struggle. The other ones were there, but it just wasn't allowing me. The ones that we have used in lab has been more like this one here. We've used that one in lab, right? You rip this off, dump that in the liquid, and then compare the color with one of these here. That's what I was trying to show you guys earlier, but it was not allowing me to drag just the one picture. Okay, we finally got it. Okay, let's go ahead and move on. So of course, when the pH is low, and you know the scale, right? The pH scale, they're saying low and high, that's all relative. The scale, in the middle of that scale, you have what? 17, and not 17, sorry, 7. 7 is neutral. And then a pH below 7 will be acidic, right? So we have 0, 1, a pH of 0, pH of 1, pH of 2, pH of 3, pH of 4, 5. Oh my goodness, this is so crowded. I thought I kind of said a lot, but okay. Let's see. Let me add a page because this is crowded even for me. So we know about the pH scale. The pH scale goes from 0, 1, 2, 3, 4, 5, 6, 7. So from anything 7, less than 7, that tends to be acidic pH, right? And in the acidic range, the pH of 0 is very acidic, very acidic. So when you're going left in the pH scale, at least based on what how I wrote it, you're going towards the more acidic side. And of course, 7 stands for pH of neutral. And then when you're going above 7, you have 8, 9, 10, 11, 12, 13, 14, right? The 14 being the most basic. So if we're going to the right, we're of course going from neutral or more acidic towards the basic side, okay? So when they say here low and high, that's what they mean relative to a neutral or just relative to something else. So low pHs in general, the ones that are less than 7 tend to be acidic, and because they have a lot of hydrogen ion. High pHs tend to be basic, they have a lot of hydroxide ion, okay? Oh, I guess I said it here in words, less than 7, more than 7. Of course, when you look at the compound water, right? Now I said here, water releases both hydrogen ion and hydroxide ion. It's not just that. Water has the formula H2O, right? If we expand that formula and look at the Lewis structure, you can look at water like this. The Lewis structure shows you water as a band. Lewis structure doesn't show you as a band. This is Vesper model. But anyway, you can look at water as OH, right, attached to H, like that. So when the bond breaks here, for every one water molecule, we get equal amounts, right? When this bond breaks here, we get an OH negative, and from this side here, we get an H plus. So for every time a water molecule, the bond breaks or it ionizes, water ionizes. So this is water ionizing, right? So when water ionizes, we get one base ion for every one acid ion. So water is both basic and acidic at the same time. For that reason, we call it neutral, because essentially the base cancels out the acid. So it's neither nor. Okay? So water will be neutral. Does that make sense? Okay. So I think I covered that. And for that reason, water has a pH of 7. Okay. I kind of really covered Arrhenius definition. Now we're moving to Bronsted-Lowry definition. So I'm going off script and then we'll go back to the text, right, of the PowerPoint. Bronsted-Lowry definition. These are actually two scientists, not one person with the first name and last name. It's two scientists. In Bronsted-Lowry definition, this definition is a little bit more detailed in the sense that I should say the definition of the acid is based on its action. Technically, so is Arrhenius, right? But we identify the acid because it transfers a proton, an H plus, to the other reactant. So, of course, it's implied back here in a chemical reaction, an acid will do something, it reacts, right? Over here, our emphasis is the mechanism, how it's reacting. We will judge a chemical to be an acid when it transfers a proton. So remember, the proton is H plus. So you're probably wondering, right? I know I'm giving you guys a lot of details based on my experiences of teaching. Somebody asked me, why is it a proton? Let's look at the hydrogen atom, right? The hydrogen atom has got a proton. If you look at the atomic symbol for hydrogen, does anybody remember what it was? So hydrogen, I think, I'm trying to remember because it's been a minute since I've written this down. Is 1, 1. So hydrogen is 1, 1. Just a regular hydrogen. Of course, you have deuterium, you have tritium, you have isomers of not isomers. You have isotopes of hydrogen, other ones, but this is just basic hydrogen. It's 1, 1. And the 1 up here will be the mass number. Mass number tends to be equal to number of protons plus neutrons, right? And since it's 1, then hydrogen just has 1 proton. So for hydrogen, number of protons are equal to 1. Number of neutrons are equal to 0. I also know the number of protons is 1 because this is the number of proton, right? Number of protons, so it is 1. And so based on that, the number of neutrons is going to be implied to be 0 because if it was anything other than 0, then the proton plus neutron should give you 2, correct? If it was at least 1 neutron, but it's 0. Okay, and then we know hydrogen has got 1 electron. So I don't even need to draw that. Hydrogen has 1 electron. So if that's the case, if hydrogen loses the 1 electron to form H plus, so if you have a hydrogen atom forming H plus because it lost that 1 electron, right? This got released. Since there's no neutron, the only thing that's left here is the proton. And that's why that H plus is called a proton. When I was in school, the teacher kept calling it proton, and I'm like, okay, maybe it has 2 names. You know, sometimes you're called Karen, and then you're called Sissy by your little sibling, right? So people can have 2 names, but the reason, this one does have 2 names, but the reason why it's called proton as like a nickname is because when the electron is lost, all the subatomic particle that's left behind is called a proton, okay? Okay. Now that I've done that lengthy explanation, let's move on. According to Bronsted-Lowry, we see an acid in its action, okay? So we can't just jump to something and say, hey, it's an acid, it has a hydrogen, even though that's kind of a prerequisite, right? The acid has to transfer hydrogen ion. For it to transfer hydrogen ion, or it has to donate. So here it's saying transfer, or you can see the term donate, right? But the acid donates or transfers protons. So I've seen some books that call this donate. So you cannot donate something that you don't have, right? So if the acid is going to donate a proton, that means it has to have a proton. But the base here is not judged according to the presence of OH. The base is the one that accepts the proton. So in Bronsted-Lowry definition, the one that is kind or benevolent is the acid, and the acid is able to give what the base desires. The acid gives the proton, the base is the one that's seen as, the one that's needy. It accepts the proton that was given, okay? Now, the one thing I have to say about Bronsted-Lowry, while the definition is a little bit complicated, you can make assumptions about what the acid is But the best way to know that the acid is an acid is for you to see in the formula that it is donating. Okay. So what I mean by that here is, let me go ahead and I'll just re-explain this part here. So HF, we can make assumptions, right? That HF right now, the way this is written. Oh, before I forget, let me go back here. I almost forgot. In Arrhenius definitions, the acid forming the acid ion tends to be a one-way reaction. So we use the one-way arrow like that. This one-way arrow. Do you see that? The one-way arrow like that. In both forms, the one-way arrow like that. The one-way arrow like that. Oh, this wasn't even defined as an acid, but you get the idea, right? In Arrhenius, the acid that's breaking down, we show it using a one-way arrow. In Bronsted-Lowry, when we're looking at the acid, we use two-way arrows. We tend to use two-way arrows most of the time, right? To illustrate the acid. So where was I? Yeah. So when we're seeing this, especially when we have a weak acid, because I'm trying to remember what I said. It's been a while, but yeah. Especially when we have a weak acid. If we do have a strong acid, we have to use a one-way arrow. Okay. But if we have a weak acid, we have to use a two-way arrow. And I'm getting ahead of myself. We haven't covered that yet, but you see how that plays out later on. Okay, so this is a weak acid. We'll learn that in a little bit. And so you see here that this forms F minus, and then it forms H3O plus. Okay. If these were missing, we could speculate that most likely this formula here is an acid, right? So if this is an acid, that means the mechanism of reaction, how it plays out in the reaction, HF will have to give its H plus. So it donates its H plus to H2O, right? And so after that happens, you go from a neutral compound. So remember the compound here has hydrogen ion, H plus, and then fluoride ion, F minus. So the H plus is the one that gets given to this one here. So what we have left is not a neutral ion anymore. Now we have F minus present, and this would be, of course, F minus AQ, okay? And then the H plus then joins the water. So the water formula, I know I showed you guys this earlier, it's like this, water, right? You have two lone pairs here. This H plus comes and attaches itself over here. The lone pair here gets used to make a bond, and you have positive. So we have H3O plus AQ. If these are too much, just remember the most important thing. When you have a weak acid, you tend to add it to water. You have an equilibrium right here, and then you have whatever you define as an acid has to be the one that gave up the proton to form this. And then, of course, this one here will be the base. So I'm going back here and I'm defining the acid as the one that lost the proton, right? The acid is the one that transfers or the one that donates. So this is acid. Why is it an acid? It donated or transferred the proton. How do I know that? After the transfer, it doesn't have the proton anymore. And this is the base. How do I know this is the base? This is the base according to Bronsted-Lowry because when the transformation is done, it has an extra proton it didn't have before, okay? So according to Bronsted-Lowry, this will then be the Bronsted-Lowry acid, okay, according to them. This will be the Bronsted-Lowry acid based on its actions, right? And then this will be the Bronsted-Lowry base, okay? And these for now are the products. So we'll see later on that these products are not called, they have a specific name. The negative ion, the remaining ion, which is negative, that was formed when the acid gave up its hydrogen, is called a conjugate. It's a conjugate base. And it's base because it's more negative compared to the original acid. And this one here is called the conjugate acid. And this is more positive compared to the original compound, right? And so I feel like I just find myself wanting to unpack so much, but we're supposed to just be defining, not teaching the whole lesson. So I'm going to move on. The final definition of the acid that tends to be a lot broader is Lewis definition. In Lewis definition, this is a very broad definition. This is not a very common definition, okay? So when we have an acid here for Lewis, remember Lewis, the guy with the dots, right? He's the one who has the whole Lewis structure of water looking like this. We're talking about that Lewis. Yeah, him, the one with the dots. So when he comes in, he says an acid is an electron acceptor, okay? And then a base is an electron donor, okay? So I'm going to come back and look at this here. I want to go ahead and go back to the beginning. Okay, so we're back here looking at the definition, the overall definition. In Arrhenius' definition, both the acid and the base are giving up something, right? The acid gives up hydrogen ion, the base gives up hydroxide ion. In Bronsted-Lowry, though, it seems like the acid is the one that's donating, right? The acid is, so you have the one that has and the one that doesn't have. The one that has is given to the one that doesn't have. So the acid donates its proton, the H plus, to the base. And the base becomes a substance that is happy to accept what the acid is giving up. When we go to Lewis' definition, it's actually the base that is donating something. Remember, in Bronsted-Lowry, it was the acid donating proton. In Lewis's definition, it's the base donating something. What is the base donating? First of all, the base has an electron pair, right? And then it's able to donate that electron pair to the other substance. So base, according to Lewis, number one, has, I can't spell has lone pair electrons. That's the first requirement. Number two, donates it. Okay, what about the acid? Has no lone pair electrons that are extra. It doesn't have a lot of lone pair electrons that are extra. So the space where the lone pair electron should have been is actually empty. So it has an empty orbital. Okay, but why it doesn't have the lone pair electrons it desires, it will take your lone pair electrons if you're willing to offer it. So the acid actually takes from the base. It will accept lone pair electrons. It's not picky, but it needs the electron pair, okay? It needs that lone pair electron. So let's go ahead, go back to the slide I was on so we can continue to unpack this. We're continuing to unpack the mystery that is these elements, right? We're trying to make sense of their behavior. Why do they behave the way they do? Why do they react the way they do? Because we're trying to understand them. Okay, so I think I was right here, right? From Lewis's definition, an acid tends to have an empty orbital. So when you're trying to identify if something is an acid, what you're looking for is not H plus. The acid here is not defined by the presence or the absence of H plus. We are looking for an empty orbital. So you have to be able to recognize empty orbitals. It's a little tricky because you're recognizing emptiness. You're recognizing missing electron pairs, right? So how do you recognize something that's not there? We will review that towards the end of this chapter. And I already have the video recorded so you can watch that, but you're recognizing empty orbital, right? And we're told here, because it has that empty orbital and it wants to fill it with electrons, the acid tends to be an electron pair acceptor. And it wants pairs, not one. It wants a pair of electrons. So it's the one that's needy. It wants an electron pair. So it's not the aggressor because it's the needy one. But the base tends to be the aggressor because it has what the acid is looking for. Okay? So the base is generous. The base tends to have a lot of electron pairs. So in this case, for the base, let me try to separate that part. When we're looking at the base for the Lewis base, we want to locate electron pairs. So when it says here, look for electron pairs, it's not saying the base is looking for electron pairs. It's saying for you to recognize the base, actually, let me use a different term here. Recognize lone pairs. Now, many times the empty orbital here has to be on the central atom, right? Most of the time, central atom. So you want to recognize the empty orbital on the central atom. For the base, you want to recognize the electron pairs on central atom. Now, I mentioned this in 1411. The central atom is the atom of focus. Usually, it's the one in the middle of the whole formula, but sometimes it's the one at the edge. When you go to organic chemistry, the central atom will be the atom that you're focusing on, whether in the middle or at the peripheral, at the edge. Yeah, that can also have lone pairs. Okay, so here we're seeing, oh, I'm seeing the example of Lewis base. Let me finish that thought and I'll go back to the acid, right? In the Lewis base, yeah, I didn't give the original video. Okay, anyway, this is a new video. Here, this is a Lewis base, right? Now, when you're looking at the formula, this is the formula right here. Can you see lone pairs? No, you can't see lone pairs. So how are you supposed to just look at that and say, oh, that's a Lewis base? I mean, you could say it's a Lewis acid, but it's not. So for you to recognize the Lewis base, you want to take the formula and draw Lewis structure. Oh, my mind is going places because I'm sitting here thinking, is Lewis setting us up to try to draw his structure so we can answer this question? No, he's not. I don't think he's thinking that deep. Draw a Lewis structure to recognize the lone pair on the central atom. Since we have a lone pair here, this can act as a Lewis base through the central atom because nitrogen can donate these lone pair electrons, right? Lone pairs to acid. Okay. Now, I did not give you guys an example of a Lewis acid. I have to give you an example of a Lewis acid, the one that's an electron pair acceptor. The very common one is BH3. So I'm going to draw BH3 here because I need this space and I don't want to pull up a whole new. Yeah. So I've already explained that part, right? So for BH3, when you draw the Lewis, oops, not that. When you draw the Lewis structure, BH3 is the formula. Once again, BH3 looks very much like NH3, right? But once you draw the Lewis structure, you see how different they are. In the Lewis structure, you have boron, that's in group 3, and we have, no, sorry. It is in group 3, but we have one atom in the compound, in the formula, and it's in group 3. So we have 3 electrons. Hydrogen, we have 3 of them in the formula, right, in the whole formula. And these are from group 1. So we have 3 electrons here. Total electrons, we have 6. Lewis structure, put B in the middle, surrounded by 3 H's. H, H, H. Draw single bonds using the electrons here. 2, 2, 2. I use all 6 electrons and left with nothing. You do not double bond this. Don't try to double bond this because, first of all, hydrogen has no lone pair to help to form a double bond, right? So hydrogen has no lone pair to justify the formation of double bond. Don't just feel sorry for an element and double bond stuff, right? You gotta follow the procedure. So this is it for the Lewis structure. This is it. But if you look at boron, boron is kind of obeying the sectet rule. It is surrounded by 6 electrons. So boron currently is surrounded by 6 electrons. So we covered this in 1411. Of course, this is the structure, right? So that boron has not reached octet. So technically, boron has room for 2 more electrons. Because there's an orbital here that could be filled, that's empty. So we're going to identify this as empty because there's no lone pair, right? Empty, empty. The P is silent. The empty, right? So boron could actually take the lone pair, not really take the whole thing. It can form a bond with nitrogen by sharing that lone pair, right? Man, I'm just getting to the end of this chapter. No. You guys will cover that later on. I'm just showing you, right? It's a relationship that is mutually beneficial to both reactants, the acid and the base, with the acid being the acceptor and the base being the donor, right? Mutually beneficial relationship. Okay, so I think I wanted to hear, metal hydroxide is the format for Arrhenius base, right? And the metals here that form the hydroxide, these are group 1 and group 2 hydroxide. I already talked to you about, the format of how the acids are written. So I wanted to go over that again. The one thing I'm mentioning here that I mentioned in the past was For most general chemistry acids, the hydrogen is written first and then the rest, right? It's called the ionizable hydrogen. This is the hydrogen where that hydrogen, the bond breaks here and then that hydrogen gets released in water. The rest of this part here remains intact in water. So you see that for the most part like this, HC2, H3O2, and then this is a weak acid. So when it breaks apart, it releases H plus, and then the rest of it remains intact because it breaks right here, right? C2H3O2. This has to be minus. So together they form a neutral compound. Does that make sense? Those of you on campus, we're going to be doing a lab. I think it's I3, right? That analyzes the ionization of acetic acid, that acid. This is how we write it in Gen Chem. When you go to organic chemistry, those of you who are going off to organic chemistry, the same acid is written like this. Organic chemistry focuses on the compounds formed by carbon. So the emphasis here is compounds formed by carbon. And this is showing you how the bonding really takes place. While this one here is more of a molecular formula, right? So most of the time, acids have the acidic hydrogen in the beginning. Once again, this hydrogen here is called the acidic hydrogen, the one that gives the original formula acid properties, the one that gets released first in water. I forgot to put AQ here. I know, so many details, right? This is chemistry for y'all. The acidic hydrogen may be placed in the beginning of the formula or at the end like this. This is more common for organic chemists. And this one here is more common for Gen Chem people or inorganic chemists, people who are not focusing on organic chemistry, okay? Either the beginning or the end. Okay. Once again, H plus or H3 plus represents acids, right? And then OH minus represents base. Okay, so now I can move on. Man, I'm just now moving on along the slides. Okay, as I mentioned before, for areneous acids, they tend to produce H plus. This is shown right here. You see the one-way arrow, same thing with the base. But this is true when you have a strong acid. And so later on, we'll talk about this as being an example of a strong acid, this being a strong base. Okay, this is the mental model. For those of you who are going to be doing the face-to-face lab, the mental model here is showing you that the acid releases H plus. And the H plus here is that acidic hydrogen, right? The one that's acidic hydrogen, right? Actually, the only hydrogen. And the acid ionizes. It breaks apart to produce ions. One of the ions happens to be the hydrogen ion. The other one happens to be the chloride ion. So it's the positive ion that makes this an acid, because that's the acid ion. On the other hand here, sodium hydroxide produces OH minus. And the OH minus is what makes this, once again, a base. Because the OH ion is the ion that represents base. Okay. So here we're told hydrogen ions from the acid combine. Oh, this is in the context of a chemical reaction. So we're looking at Arrhenius acid-base reactions. I forgot to read the title, y'all. So hydrogen ions come from the acid, right? And combine with hydroxide ions from the base, making a molecule of water. So think of H2O as hydrogen combined with hydroxide. Remember, the hydrogen was positive, the hydroxide was negative. As they form the ionic molecule or compound, they neutralize each other. This reaction is called neutralization. In a neutralization reaction, the cation from the base, right, combines with the anion from the acid. So example given to us here is we have the HCl, that's the acid, the NaOH, that's the base, and you have a double displacement type of reaction here. Double displacement. I remember being in biology and learning that acids and bases form salt and water. That's true if the definition is Arrhenius. So I want to say here, when we're dealing with Arrhenius, with Arrhenius acids and bases, yes, usually form salt and water. But when you come to Bronsted, Lowry, and Lewis definition, it becomes a little bit more complicated, right? So when you have a strong acid and a strong base, yes, you get salt and water. Okay. So our example given to us here was what? HCl plus NaOH. So going back to double displacement reaction, we said in 1411, the mechanism of this reaction is it ionizes and then you have crisscross. So the ionizing here is the H ion is formed and it separates from the Cl minus ion. Then you have Na positive ion and then OH minus ion. So you have the sodium ion going after the chloride ion, right? This combines with this. Let me put it like that. And so that's how we get the salt, NaCl. And over here, you have the hydrogen ion and the hydroxide ion combining like that. So we get the H2O like that. Okay? Okay, we're defining pH, right? So pH is a logarithmic measurement of the hydrogen ion amount. So it's a log measurement of the hydrogen ion concentration. So all it's saying is that when we're measuring the pH, we're measuring the amount of hydrogen ion, but by using log. So even though this is what we're measuring, the actual calculation being done to produce a number to us involves log. That's all it's saying, okay? So when you have many hydrogen ions, you end up with a low pH. When you have many hydroxide ions, you end up with a higher pH. Does that make sense? And since the reaction is called neutralization, in this case here, acids have low pH, bases have high pH. When you have this kind of outcome, the salt is neutral pH, so neutral pH, and the water is neutral pH. So this reaction is called neutralization because you're making a neutral product, right? You started off with non-neutral reactants, but all of a sudden, either product is neutral, okay? And you can see here, in both cases, you're forming water. No, I mean, I should say both. In all cases, you're forming water, 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 right? So this is neutralization reaction, and the pH here is going to be equal to 7. So I'm moving on. So I'm going to show you guys, of course, the Bronsted-Lowry acid example here. I already told you the acid is the one donating the hydrogen ion, and the base accepts the hydrogen ion. So I won't spend too much time here. I already defined acid and base, right? So please notice, you will be given a question where you have to identify the acid, the base, the conjugate base, the conjugate acid. Please notice the conjugates are both products. They're usually products. And then, of course, you have the Bronsted-Lowry acid and then the Bronsted-Lowry base, okay? Those tend to be the reactants. And so how do you judge what the acid is? It's easier if only one of them has the H. If one of the reactants has the H, the other one doesn't, then it goes without saying the one that has the H will be the aggressor, the one that gives up its H. But if both formulas have H's, then you have to recognize which is which, right? In this case here, in this example, you can see, hold on, give me just a second to copy this part here. You can see only this has an H. This one doesn't have an H. So the B cannot be, and this is supposed to be negative here. Oh no, it's neutral. Ooh, it's neutral. Okay. The B cannot be an acid because it has to donate a proton. HA will donate its hydrogen ion, right? So donates hydrogen ion because it's the only one that has a hydrogen ion. And when you look over here, the H plus is lost. So you know for sure, yeah, once it did the donation, this is what's left. And then B plus or B accepts H plus, right? So the way they're paired here, the way they found each other, the one that wants to give looks for the one that's looking for. Once again, it's mutually benefiting each reactant, right? The donator wants an acceptor, so they're paired together. And then, of course, you can see what it becomes, right? So here you have the conjugate And if the reactant was an acid, we define it as an acid here, right? A Bronsted-Lowry acid, whatever is left over after the donation is called a conjugate. In this case, conjugate base. So it's the opposite of what the original reactant was. This one here is a Bronsted-Lowry base. So when it accepts the proton, it becomes a conjugate acid, okay? One other way for you to identify the acid from the base, when the acid loses the proton, it becomes more negative. So acids become more negative. You see, it went from being neutral to negative, and then bases become more positive when they become acids, when they accept the proton. Okay, so hopefully that makes sense. We're trying to label this part. Once again, acid donates proton, base accept proton. Look at what happens on the right side to determine what kind of molecule you're dealing with. Okay, so before we get into actually looking at the chemical reaction, here we're looking at identifying what is relatively the acid, and then what's the conjugate base, and then vice versa. Okay, so all reactions fit the Arrhenius definition, also fit the Bronsted-Lowry definition. So if you have a reaction that fits Arrhenius definition, that reaction also fits Bronsted-Lowry definition. In Bronsted-Lowry acid-base reaction, the original base becomes the conjugate acid. That's what I was trying to communicate earlier. In the reverse reaction, the original acid also becomes the conjugate base in the reverse reaction. Okay, so acid becomes conjugate base, base becomes conjugate acid. So this is a difference, right? If you define something as a base, which in this case, this is defined as a base, the base has to accept, right? It has to accept the hydrogen ion according to Bronsted-Lowry. So to figure out the formula of the conjugate acid, you have to add an H and a plus. So, it's over here. So this is the original base, this is right here. And this is showing us how you're adding an H. So the final product will be N, the number of N has not changed. The number of H's have changed. You now have an extra H. So it went from 3, right, to 4. And then the compound went from neutral. Now you have replaced the H plus, the H. Now we're about to place that plus. The plus goes over here. Okay? So the way it works here is a number line. The number line I drew on the bottom, but I'll do it right here. From -3, -2, -1, 0, +1, +2, +3. When we start with a neutral compound and we're going to the acid, going towards the right is more acidic as far as the number line is concerned. Remember I told you when you're creating an acid or you're becoming more acidic, it tends to become more positive. The reverse is becoming more basic because bases are more negative compared to acids. Acids are usually more positive. So when you add the H plus, you start with 0, you end up with a positive ion, just one positive. Does that make sense? And that's what I started with NH3, no charge, and ended up with NH4, positive. Okay, here. With the base, we're starting with water, and then we're removing the H plus because base, sorry, this is not base. With the acid, you're starting with H2O. The acid is losing or giving up the H plus, and we're ending with OH minus, right? So see how that plays out right here. Water is behaving as an acid here. How do we know that? It donates its H plus. So water starts off neutral, but it gives up an H plus. So it ends up -1. So here's when remember you're adding H plus, it goes from 0 to more positive. The reverse is you're losing H plus, right? So it starts off neutral and it becomes OH negative because it's losing an H and a positive. So you have one less H and it went from neutral to negative, okay? Over here, once again, this is an example of what we just saw. You're gonna judge the acid based on what the product has, right? So over here, I know we see the base, right? But if this label was not provided here, you start with one start with one N. Oh, I'm getting tired. Start with one N, we still have one N over here. You start with 3 H's, now we have 4 H's. So you can say from here to here, we added on. So we added on one H and of course a plus because the H and the plus coming together. So that means NH3 it accepts H plus, correct? To become N, one more H, and the positive that wasn't there. So you can tell that. Okay. If you found the one that accepts H plus, that means the other formula has no choice but to donate H plus because they can't both be acceptors, right? Something has to give, the other one has to receive. So this one is going to be the Bronsted-Lowry acid. This would be the Bronsted-Lowry base. You can see the acid is the one that gave up its H plus, right? Because here there's one, from here to here, there's two H's, here to here, there's only one H. So it lost its H, and this was neutral, and it went negative. So it went from 0 to -1, that's definitely base. And this one went from 0 to +1, definitely acid, right? So a base will accept a proton and become a conjugate acid. An acid will donate a proton and become a conjugate base. The acid becomes the conjugate base, the base becomes the conjugate acid. Hopefully that's clear. And this is the number line I showed you guys earlier. So I'm going to be doing some practice problems here. In this problem here, we're told it's practice, right? Write the formula for the conjugate acid of the following. Oh, this one here has answers. That's okay. You can see right here, right? From here to here, you added an H, and then there's an extra positive, so the positive. Here, because you're trying to create a conjugate acid. That's the product, right? This is a conjugate acid, implying that the original one here was a base, right? The formula on the left was acting as a base. Base accept protons. So you're adding a proton. Okay, once again. So you're adding H and a positive. So this goes from still having one N, but now it has an extra H, so NH4, and the positive. So it goes from 0 to positive because we're dealing with going from base to acid, right? Here it has no H. It ends up gaining one H and a positive. So you see that? H. The H goes in front of the rest of the formula. And how do you know what the charge is? You start off with -2, right? Just move one spot and you become -1. That's how we get this one here. And then here we have H2PO4, one negative. And then once again, add an H and a positive. So you go from H2 to H3. And then the negative becomes neutral, which is 0. We don't write the 0 here, it's implied. Okay. So I gave you guys some problems where the answers weren't obvious. Let's go ahead and work on this one here. In this one here, once again, we're starting with a base. We have to write the conjugate acid, right? Let me separate this part here. This is our own problem. So we're gonna add an H plus, right? So as far as the charge is concerned, we're going from -2 to -1 because it says here it's negative, right? Because you're adding an H plus, so you're going to the right, more positive. But we also have an H. So I'm gonna put the O and put the H here, and then negative. So it becomes OH minus. You'll see that? It can't still be 2 minus, so it's gonna be minus. Because the positive here neutralizes one of the negative. Here I'm gonna add an H plus also, that's the process. And we get N, and then we have the 1H. And as far as the number goes, it goes from -3 to -2. So it's going to be -2. Okay? Or if we want to stick with that format, we can say 2 negative. Either one is fine. Over here, we add an H and a positive. So for that one, it would be what? You add the H to that. So now we have 2 H's, right? CO3. That number doesn't change. And this went from -1. Since we're doing acid, it goes to 0. We don't write the 0, it's implied. For this one here, we're adding an H and a positive. So we write HPO4, right? You add the H in the front, that's where it usually goes. Some people put it in the back, but mostly it's supposed to be in the front. We go from -3, let's see, over here to -2. -2. Now the question is, since there's a negative here, can you keep adding H's to this? Yeah, we can add H's to that. See, I wrote here acids are more positive. you can add an H to that. When you do, you get H2PO4. This time it goes from -2 to -1. See? So it's like this one here, right? Then you can add it again. So you can go from here to here, to here to here. Then you can add the H plus again. And then finally we get H3PO4. Kind of like what we had over here. Okay. Are these further questions? Okay. Add H plus once again. Over here, this goes from negative to 0, right? So we consolidate the H's, it becomes H2 and then O. Don't write the 0. The 0 is implied. We don't write it. You just leave it and we know. Here, add the H plus. The H consolidates to that one here, so we end up with H3O. This goes from 0 to positive because we're going to the right of the number line, 0 to +1. Same thing here, H plus, we go from, this adds to here, and H4, and this goes from 0, right, to positive because we're going to the right, +1. The 1 is implied. Okay, then here when you add that here, goes HCO3. This goes from -2 to -2 to -1 because we're going to the right of the number line from -2 to -1. Then here, add the H plus here. We get what? H2, because now this adds to that. CO3 goes from -1 to 0 because we're going to the right of the number line, right? And this last one over here, this is like the other one I worked out, H3PO4, from -1 to 0, okay? I'm just trying to work out the problems I did way back when. Okay, this one here, now we're doing the opposite, right? It says write the formula for the conjugate base. That means that these are acting as acids, and they want you to get the conjugate base. So we're going to the left of the number line, not to the right. So you start from 0 here, and you're moving left. Okay? You can see why that's negative. You're removing the H and the positive. So you're removing one hydrogen, so you have one left. Then it goes from neutral to negative. So this is the reverse, right? Same thing over here. You're moving an H plus. So you're moving to the left from 0 to -1. From 0, that's implied here, to -1. That's the charge. And the number of atoms, N doesn't change, but H becomes 1 less than what it was before because you're removing one H. This one here has no H to remove, so it doesn't work. That's why it doesn't work. This one here, I don't know why it was repeated twice, but you have 2 H's to pick from. Pick one, and it goes from -1 to -2 because you're going from -1 to -2, right? As you remove the positive, that's how it plays out. Oh, I gave you guys more examples here. Ignore the answers. Look away, look away. Okay. Same thing over here, conjugate base. Okay. You start with the acid being H3O plus. So we're starting with plus. You remove the hydrogen. So you're left with 2 H's out of the 3. The oxygen number doesn't change, but the +1 now moves back at 7. It becomes 0. We don't write the 0 as implied, right? So H2O. This one here also, the N doesn't change. The H's, you're down to 3 because you lost 1. And then the positive that was here also gets removed, so now we're neutral. So we go from +1 to neutral, right? 0. Here also, the 1 H that we have is gone, CO3. And then we have negative, right? -1. We're going to -2, so -2. So bases are relatively more negative, and the acids are relatively more positive. Okay. Well, I gave you guys more. Oh, that's the same problem I was talking about earlier. Okay, let's see. Oh, I'm close to the end. I'm close to the end. Yes. Sorry, y'all. It's yeah. Close to the end. So this is what I'm telling you. Like, you have to know the whole picture, right? With this one here, you have to know the whole picture to know how the acid behave. How the formula behave for you to judge it as an acid or a base. You have to know why is this not erasing? Let's see. Okay, I guess I was doing too much. I'm trying to finish this thing because this is my weekend. I'm trying to get to the end of this so I can post it. So y'all who are getting ahead can get ahead, right? Or y'all who are reviewing can review. I'm just trying to get done, y'all. Okay. So in this problem here, like I mentioned earlier, you will be identifying the Bronson-Lowry acid and Bronson-Lowry base. Those are the reactants, right? As I mentioned before, these are reactants. And their conjugates. These are the products. So we're given the reaction. This is a one-way reaction. Later on, we'll talk about the 6 strong acids. This is one of those 6 strong acids. It's usually a one-way reaction. Okay. This one here is a two-way reaction. So this whatever is acting like an acid here is going to be a weak acid. It looks like, yeah, I'm getting ahead of myself. Right. So one-way arrow here, two-way arrow. Okay, let's go ahead and make the judgment down here. Let's start with this. Oh, this is the case I was telling you guys about. It's a little bit complicated because both chemicals have H's in them. So which one acts as an acid? Well, if you go solely by the 6 strong acids, and this one here is a strong acid, it will be the one acting as an acid. But the easiest way to have a system to help you so that even if you're not sure if it's a strong acid is to look at the products and look at the one that has one less H. This one here. It had 2 H's, now it has one less H. It only has 1 H. That's the one that donated is H plus. Okay? So we found our culprit. This right here is the Bronson, I'll call it BL, Bronson-Lowry acid. Why do I say that? It started off with 2 hydrogens, now it only has 1 hydrogen, and it was more neutral, now it's negative, right? So this lost or donated is H plus, because now we have 1 less H in the product. And because of that, it's our Bronson-Lowry acid done. And then whatever product it formed is the conjugate base. You see that? That's how they're paired. And this part right here is, if this is the Bronson-Lowry acid, it has to go with the Bronson-Lowry base. But let's confirm it's the base. It started off with less hydrogen, 2. It ended up with more hydrogen, a 3rd one, right? Where did that come from? Because it accepted the donation. So this one here accepts the H plus. That's how it got us the extra hydrogen here and the positive charge. Okay, so this is called conjugate acid. The conjugate acid tends to be more positive. The conjugate base tends to be more negative. So that's consistent with acids in general being relatively more positive than bases. Okay. There's so much to unpack about the acids. Okay, over here, we're like, hey. So in the first equation, you see how water behaves as a Bronson-Lowry base, right? According to the balanced equation, yes. It acts as a Bronson-Lowry base. And this one here acts as a Bronson-Lowry acid. Let's see how water plays in the second equation. This is supposed to be equilibrium arrow here. Let's see. HCO3 ended up with H2CO3. Ooh, so that one got the extra, the hydrogen ion, right? It has an extra H. So we can say this right here, HCO3, that is a Bronson-Lowry base. Why? It starts off with less hydrogen and ends up with more. And this is going to be the conjugate acid, right? By default, the water is playing the role of the acid, the Bronson-Lowry acid. And how do we know for sure? It starts off with 1 more hydrogen and ends up with 1 less hydrogen. It's going to be the conjugate base. You can see this one here donates proton. And then here accepts proton. Okay, like I mentioned, the Bronson-Lowry base and Bronson-Lowry acid tends to be reactive. These are reactants. That's something I had to be observant of when I was a student because I was thinking, oh, they could be anywhere, and I'll get it wrong, and I'm like, snap. Okay, the conjugates are products. Though if the reaction reverses, the conjugates can be the reactants of the reverse reaction, right? But we're not doing anything that complicated. And once again, for the acid, you're going from negative to more positive in the conjugate, and then from the base, you're going from positive to more negative. Okay, guys, this is it. So this is the end of chapter 7, not 17, sorry. This is the end of chapter 16, part 1, okay? This is the end of chapter 16, part 1. Okay.